All right. Inverses of trigonometric functions. We've talked about inverses of algebraic functions. Now let's look at inverses of trigonometric functions. Fortunately for us, there's only 6 of them. And the same thing applies here. An inverse function switch x and y and solve for y. Also switch the domain and range. We've talked about sine and cosine. And we will derive the formula for inverse, the derivative of the inverse of a sine function first. But what do we know about this function? What do we know about that? What is it? What values are we looking for and what responses do we get? As opposed to that one. And this one, we enter the radian or degree, whatever format you want to enter that in. For example, tangent of 45 degrees is equal to what? 1. How is it different from this one? In the inverse functions, we enter the solution and we get the angle that matches that solution. It's inverse, it's backwards. Here I input x to find y. Here I input y to find x. It's really, this is what you're dealing with, really. What does the tangent function graph look like? Yeah, because it's sine over cosine. Where is cosine equals 0? Think of the unit circle. At which value is x equals 0? This one is 1 comma 0. This is 0 comma 1. This is negative 1 comma 0. This is 0 comma negative. Yeah, so
pi over 2 and negative pi.
right. So this is pi over 2 or 3 pi over 2 or negative pi over 2, depending on which way you're going. So at these values, we have our vertical asymptotes. At 0, it's 0. At negative pi, it's 0. And at pi, it's 0. It's an increasing function, so it stays within those boundaries. And there's like this. So we're going to isolate ourselves only to one value of one period, negative pi over 2 pi over 2. So the inverse tangent of x what that means is because it's an inverse, it's flipped across the y equals x graph line. So this one, we switch x and y, so we're bounded by pi over 2 to negative pi over 2. At 0, it's 0, and it's an increasing function. And this is the asymptotes. So the domain of the tangent function is negative pi over 2 to pi over 2, and the range is from negative infinity to positive infinity. That's for the original one. Now, for the inverse function, the domain and ranges change. What's my domain? Negative infinity to positive infinity, and the range is bound from negative pi over 2 to pi over 2. Okay, so understanding how this works, because you have to be very conscious about the changing of both the domain range as well as the x and y. Here are the definitions of what these functions are. The first one, y equals the inverse tangent of x is the number in the domain of negative pi over 2 to pi over 2 for which the tangent of y is equal to x. And we're going to do this to all of them, actually. The last four instead of sine and cosine. Y equals inverse of cotangent of x is the number in the interval 0 to pi for which cotangent y is equal to x. Y equals the inverse of secant is the number in 0 to pi over 2 unioned with pi over 2 to pi. You notice how we have open or semi-open intervals whenever we deal with these inverse functions, for which secant of y is equal to x. And the last one is the y equals cosecant inverse of x is the number in the interval negative pi over 2 to 0 unioned with 0 to pi over 2. For which cosecant y is equal to x. we'll get to an example in a second here. There's an interesting notation when it comes into the graph or the discussion of inverse functions for the secant. For secant is less than 0, for x is less than 0, for negative values, there is no agreement on how to define it. Because the graph of this inverse secant because remember, for the secant, it's between 0 and pi over 2, and then pi over 2 to infinity. So we at pi over 2, and at negative pi over 2, we have our asymptotes up here and here. So what do we know about the secant function? What is it made up of? It's made out of the cosine, but is it 1 over cosine inverse? Where is cosine? What x values can we not use here? What's the secant, the regular secant function? What is it bounded by? Let's look at that. Let's refresh the graphs of secant function also, of the reciprocal functions. The secant function is 1 over cosine. So we have asymptotes where? At pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. These are asymptotes. Easiest way is let's look at the graph of the cosine function. When cosine is 0, it's 1. When it's pi over 2, it's 0. At pi, it's negative 1, and so on and so forth. It looks like this. This is the cosine function. So it's got a horizontal and has bounds horizontally from positive and negative 1. The secant function is simply the reciprocal of that. So at this intercept, in that interval, we go the opposite direction. That's the secant function. That's the graph of the secant function. So we start off and end between 1 and negative 1. So our graph for the inverse function we go from 1 to negative 1. And then for the next half here, here's 3 pi over 2. At 1, it goes the other direction. Which is interesting. The way we look at it is what is the inverse secant function, the graph really look like? So as we were talking about earlier, then as we said, secant is, yeah, remember, the secant function is 1 over cosine. But when we talk about inverse functions, it's not the function that's reciprocated, it's the angle that's reciprocated. That's how they're related for the inverse functions. And somewhere I had the cheat sheet. So the inverse of cosine 1 over x is the same thing because we're going to be using this relationship a lot. Because remember, how are these related? Why is it pi over 2 minus sine inverse? How are sine and cosine related? Look at their graphs. A 90-degree, right? It's a 90-degree shift. So there's cosine. Sine is just the opposite. So it's from pi over 2 to 0. So to make them equal, we take pi over 2 and then shift it back to the cosine. All right. So that's in your cheat sheet somewhere. Example 1. The inverse tangent of 1 over radical 3 is equal to what? Well, let's look at what x value will make this equal to 1 over radical 3. Where's your cheat sheets? Where's our trig identity sheets? No. I see why you'd think it's, remember, tangent is made up of what? Sine over cosine. So we need the sine value over the cosine value, where it would equal, after everything's said and done, it would equal 1 over radical 3. So if the sine was 1/2 and this one was radical 3 over 2, reciprocate them, then we get this. The 2's would cancel. So this is at pi over 6. So the inverse tangent of 1 over radical 3 is pi over 6. Because this one here is pi over 6. Yes, that's the first thing everybody looks at when they look, because I see the radical 3 over 2 on the sine function and the y value. Okay, so what would it look like if we did the inverse tangent of negative radical 3? What would that one be? Right, because now that's the second one that you're looking at. That's the negative pi over 3. Why is it negative?
Because the,
Because tangent is made up of sine over cosine. In order for this to be negative, and we just went down to, we're in which quadrant now? Fourth. So in the fourth quadrant, cosine's positive, sine's negative. Yeah, so it would equal negative pi over 3. So that tangent of negative pi over 3 is negative radical 3. You have to understand how those connections work. All right, let's define our inverse function, the derivatives of our inverse functions. Even though you have them all right here, we'll show you where they come from. So the derivative of sine is cosine. We're now going to look at these, the inverse functions. So this one is just an example. So y equals the inverse of sine x to take the derivatives of these. Remember last section, theorem 3, the formula we used? Since we're looking at inverse functions, we're trying to find derivatives of them. Remember what we did last section? The formula we used? 1 over f prime of f inverse of x. This is actually called theorem 3. We're going to use that in this chapter or in this section a lot. So in this one, what is our f of x? Sine y. What is our derivative? Sine x. Sine y. What is our derivative? Cosine x. And we have the inverse. What's the inverse function? That was given. So using this formula here, to find it says to find the inverse, the derivative of the inverse, which is the derivative of inverse of sine of x, we need to find 1 over the derivative, which is cosine of x. Instead of x, we put the inverse function, sine inverse of x. So far, so good. All we're doing is plug and playing with what we have in the formula. Now, here's the problem. Remember when dealing with inverses, the cosine of cosine inverse of x is equal to x. The cosine and the inverse of it, composite function, will cancel each other out. So what we have to do is now we have to convert this into a term of sine. Since we have the cosine, how can we convert cosine into a term of sine? Do we know any conversion factor? Solve for cosine. If we solve for cosine, what do we get? That goes over there. So we have cosine squared x equals 1 minus sine squared x. Take the square root of both sides. Cosine x equals 1 minus sine squared x. So in place of cosine, I could put this whole equation. In place of x, this is my x value. So I have 1 over square root of 1 minus sine squared sine inverse of x. Get that out of the way. And we know that sine of sine inverse of x is equal to x. So that means this equals 1 minus x squared, square root. So the derivative of the inverse sine is this.
How did you cancel the sine squared times sine negative one to get 1 minus x squared?
It just becomes the squared function of it. If we square that, it becomes that. Because it's whatever happens. This is my u value. So it's sine squared is of the inverse. What this looks like is this. Sine squared, my u value is sine inverse of u times sine and the u value of the inverse. So this value goes with this one twice.
Okay, okay.
That's x and that's x, so it's x squared. It's like saying cosine squared of x is cosine x times cosine x. I didn't square x, but it's the value part of the function.
Okay, thank you.
Right. So now that is just for if we had x. What if we had inverse sine of u? What would that one equal? It'd be the same thing, 1 over square root of 1 minus u squared times du dx. And it's always because we saw for this one, and then we have to take a derivative of what's inside there, which is what that brings in. Let's look at an example of that one. Find the derivative of inverse sine of x squared. So we have what our formula tells us. We have the inverse sine of u. In our case, u is equal to x squared. The derivative of that is 1 over square root of 1 minus u squared times du dx. So we have, in our case, this is my u. So I have 1 over 1 minus x squared squared times the derivative of u, which is 2x. On top, we have 2x. On the bottom, we have 1 minus x to the fourth. There's my derivative. Cosine, let's see, where's that? Oh, we'll go ahead and do cosine also. You see, that's what we just found. We found number 19. The derivative of the inverse of sine is 1 over 1 minus x squared. Let's look at the derivative of the inverse of cosine. So how would we set this one up? We have our f of x, we have our f prime of x, and we have to have our inverse of x. The inverse of x is given. That's cosine inverse of x. So what's the f of x? Cosine x. So the derivative of cosine is negative sine of x. So this derivative becomes remember we have that. Here's the function. Inverse derivative of x is equal to 1 over f prime, f inverse of x. So plug in what I have here. F prime is negative sine times f inverse, which is inverse cosine of x. That's where I'm getting this stuff from. So the negative goes up on top. Same thing. We need to get a function with respect to cosine. So we have cosine squared x plus sine squared x equals 1. So cosine squared x equals 1 minus sine squared x. Oh, I'm sorry. Sine squared x is 1 minus cosine squared x. So sine x is equal to the square root of 1 minus cosine squared x. I can plug that in place of sine now. So it's negative 1 over square root of 1 minus cosine squared. My x is my inverse function. So that becomes negative 1 over square root of 1 minus x squared. which is the formula for cosine. All right, let's look at what happens with tangent. These are all going to be pretty much the same thing. Let's go back. In order for an inverse to exist, what has to be true about the function itself? Has to be continuous, and what else? Has to be differentiable. The derivative has to exist, and it has to be one-to-one. So differentiate this one. So we use the same rule. F prime. Don't ever get tired of writing down the rules because they're going to help you solve these things much faster. So in tangent, my function is f of x is tangent x. What's the derivative of tangent? Secant squared x. And our inverse function was tangent x. Because we need all that stuff for our function. So to differentiate inverse tangent of x dx, so we have the f prime, which is secant squared of tangent inverse. Is there a connection between secant and tangent? Well, let's see. We know our first one we had was cosine squared plus sine squared equals 1. If we divided this one by cosine squared, we have cosine squared over cosine squared, sine squared over cosine squared equals 1 over cosine squared, which would be 1 plus tangent squared equals secant squared. So secant squared is 1 plus tangent. One plus tangent squared, and my u value is the inverse function. So this one becomes 1 plus x squared. And again, the only thing different between the x and the u is we multiply by du dx. That's all we have to add to make it a universal function. The hardest part about this is what? When you plug in everything, making both of these the same value. You have to make it whatever value is inside the parenthesis. So you have to remember all your trigonometric functions and identities. So we have to convert secant squared into tangent, which is what we did. All right, now let's look at secant. Let's take a derivative of the secant. Problem. Remember what the graph of this one looked like? It was between negative pi over 2 and pi over 2, and pi over 2 to 3 pi over 2, and it started at negative 1 and 1. Because of the graph. It's much easier if we use implicit differentiation in this one. Okay, so this is what we started off with, right? Then that has to be true as well. In other words, if I took the secant of both sides, if I take the secant of both sides, then I get secant y is equal to, these cancel, is equal to x. Now we can differentiate both sides. We know the derivative of secant, don't we? We figured that out. So the derivative of secant is what from our chart? Then dy dx equals 1. The derivative of secant is secant tangent. Yeah. The derivative of secant is secant tangent. Rule number 17. We're looking for the derivative, so we have to solve. So we divide both sides by secant y, tangent y. So the derivative is equal to 1 over secant y, tangent y. Let's verify that. Ah, no. Well, we're getting close to it because this is the derivative of secant of the of inverse. We have to now put it in terms of x and y like we just like the other ones. So now in terms of x and y, so what do we know? We know that secant y is equal to x. And we know that tangent y is equal to this plus or minus a square root of secant squared y minus 1. 1, what was that one? We just did that one. So it's 1 plus tangent squared equals secant squared. So we know that. since secant y is x, then this has to equal plus or minus x squared minus 1. That gives us this value. And secant y is this value. So the derivative is equal to 1 over x square root of x squared minus 1, plus or minus, which is what our formula sheet tells us. Instead of plus or minus, we make the absolute value. Why does the x have to be absolute value? Remember the graph. The first derivative is what? Slope. What's the slope at any point on these two graphs? It has to be positive. So instead of putting plus or minus, having a piecewise defined function, I just make it absolute value of x, because that's the only thing that make it negative. X squared makes it positive, and since we start off at 1, negative 1, this is always going to be positive, so x is always going to be bigger than it. So that's what we have. So this is our formula for our derivative of the inverse of secant. And if we had the u instead of x, then the derivative of the inverse of secant would be 1 over absolute value of u squared minus 1 du dx. Again, you just change u to x to u, and you have to have a du dx. It's just a composite function. Let's look at an example of this one. The inverse secant of 5x to the 4th. Take a derivative of that. I could say y is equal to the inverse of secant 5x to the 4th. Find the first derivative. Yeah, it should work. A formula. I have the formula is this: d dx secant inverse of u is equal to 1 over absolute value of u square root of u squared minus 1 du. So the derivative of this function, what's u? 5x to the 4th. So du would be 20x cubed. So we have 1 Oh, this would be u, and that's u, so 1 over u, so it's 5x to the fourth square root of 5x to the fourth squared minus 1 times du, which is 20x cubed. Question, do we need the absolute value sign in front of this one? Can 5 ever change? No. X to the fourth can never be negative. So what we have here is 20x cubed, 5x to the fourth times radical 25x to the 8 minus 1. The 5 goes into 24 times. 3 of those cancel, so it's 1. So our answer is 4 over x radical 25x to the 8 minus 1. So that's the derivative of our function. So now that you have the formulas there, do you have to memorize them? Not really, but can you derive them? I hope. But you always have them in your cheat sheet. So inverse function and inverse cofunction identities. What's a cofunction? Ooh, long time to hear that from Trig.
You know, it's like related to like how like sine, cosine, and for cotangent.
Well, it has a lot more to do with all of the angles. I mean, what would make the angles equal?
Feel like it would like add up to what's it, 90 degrees.
Yeah, well, that would be supplementary complementary. If it's supplementary equals 180, complementary equals 90. But cofunctions are what do you add or subtract from one function to make it equal another? That's what we're looking at to deal with inverse functions. We've talked about some of them already. So the inverse function of cosine is equal to, remember the graphs of sine and cosine? How are they, what would I have to do to one function to make it look like the other? I would have to take the sine function and shift it over, pi over 2 units. The cotangent function. How are the cotangent and tangent function related? Well, they're a shift of 90 degrees, as well as the cosecant function. So why are these important? Because right up until now, we found the derivatives of sine, tangent, and secant. We can use these cofunctions to find the derivative of cosine, cotangent, and cosecant, for example. Differentiate the inverse function of cosine. So what I'm looking for is the dy dx of the inverse function of cosine is equal to the derivative of what we know already. So we don't have to reinvent the wheel. Let's just use what we know already. Because what this one tells us is take the dy dx of pi over 2 minus dy dx of the inverse of sine of x. What's the derivative of pi over 2? It's a constant. There is no value of x. So we just have to worry about the negative. Take the derivative of the other one. So what's the derivative of the inverse of sine? It was 1 over square root of 1 minus x squared. The negative out in front. Again, that's what we talked about earlier. So the derivative of arc sine is this. The negative sign just comes there. And you have you have all of them right here also. Because we just went through all of these today. All right, that does it for that section, and more so, that does it for chapter 3. We're now officially done with chapter 3. Are we? I believe so. Let me see. Let me look.